Okay, so let's do an example of cost minimization for the cup Douglas production function, the one that we've been working on for a while from now. So I wrote down the cost minimization problem. Here, the problem is we wanted to minimize the objective function, which is the cost. Now, cost of labor plus cost of capital subjected to the constraint. Here is the targeted output quantity Q0 with the cup Douglas production function. And we try to find the quantity, the optimum quantity of K and L in order to minimize this cost. So let's go with first the Lagrange. We have L equal, the objective function is the cost, KB plus LW, so price times quantity of input, plus lambda, the Lagrange multiplier, times the constraint. So here we could write the constraint again as Q0 minus A times K to the power alpha, L to the power beta, right? Let's proceed with the first order condition. By now, we all know what's happening here, right? So, first order condition, the first one is the derivative of the Lagrange with respect to K equal. Here we have 1K, so times V, so the derivative will be V plus, here there's no K, it's gone, that comes to the constraint. Lambda, okay, lambda times Q0, all constant gone, then lambda times the production function. So here it's actually not plus, but it's minus. Because we have the minus here, we multiply it. Okay? A is a constant, K to the power of alpha, so alpha times K to the power of alpha minus 1 times L to the power of beta. Rewrite. Equal 0, right? So here, for convenience, let's go one step further and rearrange it a bit. So that would be V equals lambda times A times alpha times K to the power of alpha minus 1 times L to the power of beta. And let's call it first equation. The second one is the partial derivative of the Lagrange with respect to labor, L, right? Equal. Now, the first KB has no L, gone. The second, we have W left, right? Minus lambda, very similar to above. A, rewrite again. K to the power of alpha stay the same because it's now constant. L to the power beta, so beta times L to the power beta minus 1, right? Oops, sorry, here it's a little bit tight, but that's fine. And we could also rearrange already. So W equals lambda times A times beta times K to the power of alpha and then times L to the power of beta minus 1. Right? Oops, sorry. Here should be the second. Now, and the last one, the last first order condition with respect to lambda, of course. And then that is the constraint, right? Q minus A times K alpha times L beta equals 0. I will also rearrange it already. That means Q0 equals A times K alpha times L beta. And this is the third equation within the first order condition. Now I'm sure you remember, or you have an impression what to do next. We divide 1 by 2. But here I want to divide 2 by 1. Why? We see it later. So, that will be, on the left hand side you have W over V, right? W, V equals, rewrite it, lambda A beta K to the power of alpha L to the power of beta minus 1 divided by lambda A alpha K to the power of alpha minus 1 times L to the power of beta, right? Now let's simplify things. So lambda is gone, A is gone, alpha and beta stay, so beta over alpha, yeah? Times K on the numerator is alpha to the power of alpha and denominator is alpha minus 1. So at the end we will have K to the power of 1 on the numerator, right? And then L, similar, on the numerator b minus 1, in the denominator b, so there's 1 L left in the denominator, right? And what is that? Isn't it familiar to you? We just did that in previous part. Nah? So this is the RTS L for K. And that is why I wanted to divide 2 by 1, not the other way around, because I still want, like, for you easier to keep track on, still have the RTS of L for K. However, it's still valid if you divide 1 by 2. No? In that case, you have the RTS of K for L. And here is what said on slide 8. Which is the RTS, the marginal rate of technical substitution, which is determined by the production function that the firm adopted, must be equal to the rate of the market price by which the input is traded or exchanged on the market. Yeah? So this is implied by the first order condition. And it is also said because W over V, I show you that's like the negative of the slope of the cost line, right? Because the slope of the cost line is minus W over V. So this is the negative of the slope. And this RTS, we know that before is the negative of the slope of the isoplane. So that also means that the slope of cost line, this is how I call it. You don't find it on the slide or in the textbook, but I call it that way. So equals the slope of the isoplane. That is where we see, or we find the tangent point, where the cost is minimized. Alright? Now let's move further. We have this already, we can rearrange it in the way that k, just cross multiply everything and keep k along on one side, yeah, equals w over v times cross multiply beta over alpha, so it becomes alpha over beta on the other side, right? Times L equal K, right? And I could already, for the convenience of simplification later, we see I could write it in this way: K equals W to the power of 1, V to the power of minus 1, alpha to the power of 1, beta to the power of minus 1 times L, right? And I call this equation 4. Okay, let's proceed further. By now, probably you know already what to do. We will go by substitute. Four into 3, I wrote down where we stop here, to solve for L start. That means 3 will be equivalent to Q0 on one side, the other side A times K to the power of alpha. So here is the K. First we write everything, V minus 1 alpha 1, beta minus 1 L 1. Everything bracket to the power of alpha, right? Times another L but to the power of beta. Okay. Now let's simplify that. So Q0 equal W 1 and times alpha, that is to the power of alpha. V minus 1 times alpha, minus alpha times alpha, beta minus alpha, right? And then L alpha times L beta, that means L to the power of alpha plus beta, right? Okay. Now right there, we could rearrange things like cross multiply everything else on the right hand side apart from L to the left hand side with Q. So let's say Q, but Q0, but here I already put to the power of 1, so it's easier to see later now. So W, now if you want to cross multiply to the other side, that means you divide it, and divide it means raising to the power of alpha times minus 1, so minus alpha, times V to the power of alpha times alpha to the power of minus alpha, and then beta alpha, right, equal. Now we only have L to the power of alpha plus beta on the other side. How to solve it further for L? How to get rid of exponent? Quick reminder, for example, you have x squared equal 4. How do you want to solve? How can you solve it for x? So that means x equal the square root of 4, right? But what you did behind actually here is you raise the x squared to the power of 1 over 2. And on the other side also the square root means 4 to the power of 1 over 2, right? So you raise to an inverse power of the original power. This is what we do here. So we would have to do is raise it to the power of 1 over alpha plus beta, the inverse, right? Therefore, what we would have is L, if you take 1 over alpha plus beta times alpha plus beta, that is 1, right? So L to the power 1, meaning L, equals Q0 raised to the power of 1 over alpha plus beta times 1, right? W minus alpha over alpha plus beta. V alpha over alpha plus beta. Then alpha minus alpha over alpha plus beta, right? And then beta to the power of alpha over alpha plus beta. And this is the L star already. So this is one contingent input demand function that we have solved. Now, the next step, very simple, substitute L start into where? Into 4, of course, to solve for K star. That means from 4 we have K star, can already write here if we substitute everything, equals W1 V minus 1 alpha 1 beta minus 1 and L, everything to the power of 1. So you just need to block this on the later part. So that is Q0 1 over alpha plus beta W minus alpha over alpha plus beta V alpha over alpha plus beta alpha over alpha, alpha plus beta B alpha plus beta. Okay, let's simplify it further. So that means K start will be doing it step by step. I missed something here. So here we still have A over there, right? So that is, move the equal sign a bit. Let's write A to the power of minus 1 here. So A to the power of minus 1 over alpha plus beta. Yeah, that's right. Okay, so now we have again A to the power of minus 1 over alpha plus beta over there. Now I remove it. So Q0 1 over alpha plus beta times A, before I forget it again, minus alpha plus beta times, now it comes alpha, let's put all the constant parameter before. So alpha here is power 1, here is power minus alpha over alpha plus beta, another baby box. So 1 minus alpha over alpha plus beta equals alpha plus beta minus alpha over alpha plus beta, right? Make everything like multiplied both by alpha plus beta. So that is, here is alpha beta over alpha plus beta. Yeah? So alpha to the power beta over alpha plus beta. Okay, and then beta to the power of like minus 1 and alpha over alpha plus beta here. So what is that? Again, minus 1 plus alpha over alpha plus beta equals minus alpha minus beta plus alpha over alpha plus beta, right? And minus alpha plus alpha is gone at the end, and you have minus beta left on the numerator. So minus beta over alpha plus beta, right? Then W, similar thing, W, because here 1 minus alpha over alpha plus beta. So that is beta over alpha plus beta, right? And then V, minus 1, then V alpha over alpha plus beta. So that is this case. So you have minus beta over alpha plus beta, right? And this is the second contingent input demand. It's a little bit dense here when it comes to exponent. Okay. Then we're done. I mean, it looks a bit messy, but just have to be careful, and then you'll be fine.